about Einstein, nanoscience, and superconductivity.
Thank you for that nice introduction and for inviting me to speak. I must confess that I'm a bit of a hypochondriac, and that last part of that last talk didn't sit very well. In fact, when they removed their materials, I was careful not to touch anything because, understand. Well, I do theoretical physics, so most of my work is pencil and paper and some computers, but my graduate students do a lot of computer work, and so we modeled materials. And this area of physics is called condensed matter physics. It used to be called solid-state physics. And so we try to explain and predict properties of materials. Our ancestors were the alchemists, and this was a picture drawn by Roz Chast, who is a cartoonist for the New Yorker, and this was to illustrate an article that I had written on quantum alchemy, because nowadays, with the quantum mechanics as a background, we can actually use computers to make predictions about materials. Now, the alchemists are always thought of as being the opposite of good scientists, but they were very good scientists. They had recipes for how to make things. Their theory was behind, because they thought that matter was sort of gray, and the properties that we see were sort of put on top of them. And what they didn't know is that one of the most important ideas in science is that macroscopic matter is made of atoms. You know, we all know this today, but this was not in the books at that time. And so the idea that you could build up materials out of atoms is central to not only physics, but chemistry and biology and, as I said, all of science. Now, there were a couple of models of atoms in the old days. One was by Thomson called the plum pudding model, and then Newton had a model, and I'll give you a schematic picture of this, but the modern model is the quantum model of an atom, and I'll tell you a little bit about this. In the case of Thomson, Thomson actually discovered the electron a little over 100 years ago. And he pictured the electron, which is negative, as being inside an atom. And he thought of it as a plum, and he was pulling the plums out. And since it was negative and the whole system would be neutral, the background was sort of positive. And so he would think of this as a pudding with a plum in it, and then he would pull out these electrons. Turns out that's not a terrible model nowadays, and I'll show you why later. Newton's time was characterized by people breaking things and tearing them apart, trying to find out why some things were harder than others. And so they knew that atoms had to have hooks. And if there were these atoms, then these atoms would be stuck together. They had no idea of how small the atoms were, and they had no idea about the structure, but they pictured something like this. To give you some feeling for how small atoms are, if you look at the latest estimates of the age of the universe, you get a 14 with 9 zeros after it. Now, if you say that that's the number of years that we've been around, then at least the universe has been around. If there's 365 days in a year and 24 hours in a day and 60 minutes in an hour and 60 seconds, you'll get 4 and about 17 zeros for the number of seconds that the universe has been around. If I take this container of water and just take a gulp out of it and ask what would happen if I took the molecules of water, H2O, out one at a time, how long would it take me if I did 1 per second? Well, the number of molecules in the water, in that amount of water, or even a smaller amount, is about 6 with 22 zeros after it, or 23 zeros, depending on how you count. And if I took out one at a time, it would move a molecule. If I moved a molecule per second, it would take me 1.5 million times the age of the universe to take those molecules out one at a time. So that's how small they are, and that's the concept that was so hard for people to accept in the early days. Now, around the turn of the century, Einstein felt strongly that the atomic model of materials was correct. There were many people around that time who didn't, and they argued a lot about it. In 2005, the American Physical Society and many of the similar societies around the world celebrated the 100th anniversary of 1905, when Einstein made these incredible advances. And we went around the world trying to get young students into physics, and we tried very hard to educate the public about how wonderful physics was. And if you walked up to a student and you said, Einstein is our poster person for this year, they would say, but I'm no Einstein. And so you'd have to say back, I'm no Einstein, but the University of California still pays my salary, and that it's still a good field to be in. And so, to some extent, it was useful to explain what Einstein went through at about the time when he was developing these ideas. Let me first tell you that in 1905, Einstein actually determined the molecular dimensions of sugar molecules, and I'll say something about it. He also looked at something called Brownian motion, where if you get particles suspended in space, molecules in space are knocking them all over the place. He did relativity, and he also did the photoelectric effect. The theory of the photoelectric effect was what he got the Nobel Prize for, and he thought it was his most revolutionary idea. Photoelectric effect is light goes into a metal and electrons pop out. And the question is the light that goes in actually a wave, or is the light particles? And the correct answer, if a student asks you if light is a particle or a wave, the answer is yes. And this idea of quantum theory, that all of matter is also waves, I'm a wave, you're a wave, everything is a wave, and you can think of it as a wave or a particle, was something that bothered Einstein for his entire life. And in fact, he thought more about and worried more about quantum theory than he did about relativity. And he had this famous statement that because of quantum theory, we think of things in terms of probability, as you'll see. And he didn't feel that that was an appropriate way to describe nature. And he said, the Lord does not play dice with the universe. If you asked a modern quantum theorist like me, I would say she does. And in fact, that's what we do all the time. Now, maybe in 100 years from now, people will find another way to describe what we do. But right now, there are no experiments and no ideas anywhere in physics that contradict quantum theory, which is a probability theory. Now, to show the students that Einstein didn't have it so easy, I went back and discussed his thesis proposals. He needed a PhD. He was working in the patent office and was going back and forth between the ETH in Zurich. And so he proposed to Professor Dr. Weber the idea of measuring the velocity of light using an interferometer. And he wanted to see if light had the same speed one way or the other way, depending on how the Earth revolved. And this experiment was done by Michelson and Morley in the United States, and it was the first Nobel Prize in physics to go to an American. But Dr. Weber rejected his proposal and didn't think it was worthy. And Einstein, being sort of inventive and stubborn, he went back and he decided that he'd like to investigate electrical conductance, that's how the electricity flows down a wire, and how it responds to heat. And this is a very important problem now in my field, in condensed matter physics. And again, Professor Weber felt that that wasn't an appropriate thesis. So we as professors have to realize now, when our students come to us with all these crazy ideas, that you have to be careful. We might have an Einstein around. And so he went back and he thought about thermal conductivity, which means how heat flows down a wire or how it flows through solids. And he talked to Weber again, and this is important in electronics and all the rest. And again, I'm afraid it was rejected. And in those days, they were pretty strict about the kind of paper that you use, and they had all kinds of rules. And so he wrote it on the wrong kind of paper, but he went back. And he thought about how atoms interact and form gases and liquids and eventually solids. And he proposed this to a different professor, Professor Kleiner. And this is a fundamental problem. And Professor Kleiner at the time was known for not being an Einstein fan, and so Professor Kleiner also declined it. So Einstein didn't actually have it that easy during that period. So he decided to change fields from this condensed matter fields and fields focused on materials, and he investigated electricity and magnetism, and he thought about moving bodies. And in fact, this was the work that later led to his relativity. My wife gave me this cereal bowl. A is for apple, B is for whatever, E equals mc squared. And Professor Kleiner, unfortunately, could have been famous because he could have been attached to E equals mc squared, which is on all those, T-shirts and everything when you walk around on University Avenue, either here or in Berkeley. But he didn't do it. So Einstein decided that he wanted to get involved in the atomic theory, in the molecular theory. And he made a proposal on measuring the molecular dimensions of sugar molecules. He was going to think about how you can do this and how he would explain it theoretically. And this was a very important piece of work. And this time it went to Kleiner and Burckhardt, and they said it was too short. His proposal was 17 pages. So our hero went back, and he added one sentence, and he resubmitted it, and finally a thesis. So for you students out there, you have to keep banging away at us old, sort of stuck-in-the-wool professors. At the time, this was quite important because the idea that materials were made out of atoms was central to some of the theories that were being developed by people like Boltzmann. Boltzmann had developed a theory of statistical physics, that you could describe things in terms of atoms moving around. And because people didn't like his theory and for other problems, he became very depressed and actually committed suicide. Nowadays, fortunately, we theorists don't take our work that seriously. But it was a peculiar time, and Einstein added to that time. Now, if I jump to the 1920s, we get to the quantum theory. And the quantum theory is the theory that we use nowadays. So instead of those plum pudding models and those models with hooks, we picture a nucleus and the electrons being waves and being all around the nucleus. And we can't tell precisely where the electron is. You can't just take a picture and say it's right here because there's an uncertainty principle. The more you try to localize it, the more it moves away. However, we can tell with great precision where an electron probably is. We can give you probable densities. We can give you the probability for the fact that I'm still in Berkeley now, and even though most of me is here. And that kind of theory has been very successful. So that in 1929, Dirac, who was one of the people who invented quantum theory, said that it's basically done. The underlying theory for much of physics, for a large part of physics, and all of chemistry is done. And the difficulty is only that the equations are difficult and hard to solve. But we've come a long way in almost 80 years, and I thought I'd show you a little bit about how we can predict, although I remind you what Yogi Berra said, that predicting is difficult, especially about the future. And we try to explain. So I work closely with experimentalists, and often they will come to me with their data, and I will try to explain their data, or my students and I and postdoctorals will try to explain the data. Sometimes we predict. And when we predict, and then they go in the laboratory and they try to find out whether or not our predictions are correct. And all these predictions are based on quantum theory. I should say that they often give us credit after they decide that their experiment is right and the predictions are right. And so I think this cartoon is very good. To be honest, this is the man who invented the wheel. I never would have invented the wheel if it were not for Erg's groundbreaking theoretical work on the circle. So this is our picture of what goes on inside a solid. So if you take a piece of silicon, which is the largest business in the world, you have a valley made out of it, and there are these atoms, and there are electrons that stay very close to to the nucleus. These are called core electrons. And then the valence electrons are basically spread throughout the crystal like the plum pudding model. However, a lot of them stay in bonds, and those are the hooks that Newton envisioned. And so we can actually picture what goes on inside the solid. And for example, in the case of silicon, if we put a nucleus there and surrounded it with these core electrons and let the valence electrons go through, we can calculate what the properties of this material would be. A pseudopotential is how the electrons interact with the core, and plane waves just means that the electrons can be anywhere in the solid, and that's because they're quantum mechanical. So the whole solid feels them. And nowadays, using these methods, we can actually tell you what the electronic structure is, where the electrons are. And this is for a broad class of solids and clusters and all the rest. We can give you the crystal structures. We'll tell you how strong things are, how they vibrate. And I'm going to tell you something about superconductivity, and we can also predict and explain optical properties. The question in the last 5 or 10 years has been, how can we take these models over to the nanoscience regime? Because we were working at very, very small distances, but we were talking about properties of large materials. Well, a big discovery in nanoscience that got people thinking about this was the so-called Buckyball, the carbon-60 molecule. So this looks just like a soccer ball, and it has 12 of these 5-fold rings, and all the rest of them are hexagonal. And at every interface, every vertex where these bonds come together, there's a carbon atom. These are very small again, so let me again emphasize that the relative size of these things is to what we see in everyday life is really very small. If you take the whole Earth and compare it to a soccer ball, it's the same as if you compared a soccer ball to one of these molecules. So that's how small they are. Now, this field has got a lot of push because it's a size that physicists, chemists, material scientists, biologists, engineers, and computer scientists do. In fact, we even eat lunch together nowadays and talk about problems in this size range. So atoms are down here, and that's about 1/10 of a nanometer. And 1 nanometer is about where your DNA is. And then you get a little bigger, and you get proteins and viruses and bacteria. And so this scale has brought people together to work on these things. One of the interesting structures that we work on is something called a nanotube. And the nanotube is made out of carbon, and I'll show you another one later. And it consists of the following. If I take a sheet of carbon atoms, now these are all hexagons, so this looks like so-called chicken wire fences. And there's a carbon atom at every one of these vertices. If I roll it up, I get a nanotube, and nature rolls them up. And they're very small. You can put 1 billion in a human hair. And these carbon nanotubes have captured the imagination not only of the scientists, but also of people who are trying to make devices and trying to construct things. Because they're so small, you can use them as probes. You can stick them into a cell and take them out of a cell, and the cell isn't damaged. That's how small they are. And so the biologists are using them. You can actually point out atoms, and you can feel the electrical interaction between the carbon nanotube and the atom. They are about the strongest things that we have if you pull on them this way. And so people are putting them into materials to make it stronger. They're using them to conduct heat, to conduct electricity, for filtering. And in particular, for electrical conductors, they're very interesting because they're so narrow. I mean, their radius is so small that the electrons practically exist all along the tube, and they don't scatter in the usual ways. They have unusual properties. For example, if I take one of those sheets, and that sheet is called graphene, and people are working on the sheets themselves, and if I roll it around, so I roll those hexagons around, and I go around 8 times, so I got 8 of these hexagons around in a circle when I roll my sheet, and I examine the properties of this material. It's a semiconductor, just like silicon. If I roll around 7 times and I push up one, so it sort of looks like it's going like spiral, that's a metal. You can change the properties by just the way you roll them up. And you can put the metal and the semiconductor together if instead of having two 6s, you have a 7 and a 5. And so you have an interface here that looks exactly like a piece of silicon touching a piece of aluminum. And so the idea is that with just a few bonds, a few atoms, you can start making devices. And that's why people in Silicon Valley are so interested in them. And the idea is with 50 atoms, you can build a radio. It works it's an X-ray radio, so it's a little strange. But people are working on devices. The other thing that happens is if you hook up a nanotube and measure voltage and current and let molecules fall on the nanotube, and if you put something on the surface to catch them, you can detect almost single molecules. It's a sensor. It's a nose, and it's actually better than a dog's nose. You can detect almost single atoms. So I can put sensors in this room that would measure how much carbon dioxide is coming from us. I could measure anthrax. I could measure hydrogen. And there are commercial companies that are making these things. So there are practical aspects. On the computer, first calculation, then a computer, we were able to construct a boron nitride nanotube. And these are very different from the carbon nanotubes, but they're about the same size. Instead of having carbon, 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 these are boron, nitrogen, boron, nitrogen. And the wonderful thing about these tubes is that if you put a little carbon in them, if you dope them, the electrons travel right down the center of the tube. And you can apply them for many applications. So this area has been moving along at a very fast clip. Now, there's some far-out things that are being done with nanotubes, and I'm not sure if they're going to work, and I'm not sure I endorse them, but I thought I should tell you that people have been trying to build towers to the moon for a long time, and even in the 1890s, there were ideas about whether or not you could build a tower to the moon. And there are no materials around that are strong enough. The science fiction writer Arthur Clarke, in 1945, pointed out that if we had a satellite and had it go around the Earth at just the proper orbit, it could stay over one point. So if you take Hoover Tower here, perhaps you could get a satellite that sits right over Hoover Tower. And the question is, can you build an elevator that goes up to the satellite and down? And people nowadays are talking about cables and so forth. Well, the material of choice that people are working on is, this is being done at Los Alamos, and a fair amount of your tax dollars are going to this. So if you support it, fine. If you don't, you know where to write letters. Is trying to build a space elevator. And these people are thinking of orbiting Mars and having nanotubes be the fundamental chain to allow them to get, this is the Earth here, but allow them to get from the satellite down to the surface of Mars. Now, I don't know if that will be built, but I'd like to show you something that has been built with nanotubes. Nanotubes don't always come in a single cylinder. More often, they come in a cylinder within a cylinder within a cylinder. So you get these multi-walled nanotubes. And you can pull, the experimentalists can actually pull one of the cylinders out. And if you do this, you have a bearing. And if you rotate it, you have a rotational bearing or this kind of bearing. And the friction is very, very, very small. The nanotubes are very strong. The friction between the nanotubes is very small. So you can think of using this as a motor. And I don't know, there may be too much light in here, but I hope you can see. This is a nano motor that was built by Professor Zettel at Berkeley. And this is first a schematic, and then I'll show you the real thing. So a nanotube has just gone down, and it's actually a multi-walled nanotube. There's another tube inside. So these are two tubes. And this is going to start to turn, and these things, this is gold, and they will be plus, minus to make this thing go round. Now we're going to go into the tube, and I hope at the back you can see, because inside the tube, there's another tube. And that's because it's a double-walled nanotube. you should see now. See how there's another tube inside? And what they do is they pulse those electrodes, and that makes that rotor go around, and these bonds break. And once the bonds break, this little part of the tube can go almost frictionlessly about the inner tube. And by changing the electrostatic sign on those pieces of gold on the side, you can make the thing go around. You can make it go around, you can stop it, you can make it go the other way. And in fact, this is what a real one looks like. There's a nanotube that you probably can't see going up the center. That's a piece of gold. These are the things that are going positive and negative. And this is smaller than a virus. This is the first one, and it was, now they make dozens and dozens, and they make them smaller and smaller, and they connect them up. Okay, so in nanoscience now, you can make tiny, tiny motors, you can make sensors, and it's a very interesting field. Now, superconductivity was the other example I wanted to give you, and it's one of the most fascinating fields in physics. And it happened first in 1911. It was observed first. Kamerlingh Onnes had a laboratory in Leiden, in Holland. And he was able to liquefy helium and get to the lowest temperatures that people had ever gotten to. And he asked his assistant to measure the resistance of a material as they went down and down in temperature. And the assistant found that all the materials, all the metals that he measured, the resistance kept coming down. And then he took some mercury, which was frozen, and as it came down, all of a sudden the resistance went to zero. And he thought that there was something wrong with his equipment, and Kamerlingh Onnes didn't believe it, but he accepted the Nobel Prize anyway. And the assistant went on to actually start the Phillips laboratory, which is Norelco. And so the assistant did well. But Onnes, in his laboratory, investigated many, many materials for superconductivity. And as time went on, the highest temperature they could get at that time, first of all, mercury was 1911. It was about 4.2 degrees on a scale we use, the Kelvin scale. I have to warn you that the Kelvin scale, room temperature is 300 degrees on the Kelvin scale. So this is a different scale than you're used to. But the point was, the degrees are the same as the Celsius scale, the size of the degrees. But it was going up about 1 degree every 3 years. And in 1986, 87, some scientists at the IBM laboratory in Switzerland found that copper and oxygen materials, temperature went way up. So superconductivity was occurring at almost 40 degrees Kelvin. Then people began to squeeze this, and they made another copper oxide material, and it was superconducting up here at almost 100 degrees Kelvin. Now, 77 degrees Kelvin is where nitrogen becomes a liquid. And so you could take liquid nitrogen or liquid air, and you can actually see materials go superconducting. It's still very, very cold compared to room temperature. And in fact, dry ice is at about 195 degrees. And since then, people have been going up slowly. And under pressure, you can get to 165 Kelvin. And there's a very strong effort to try to make these things superconduct at room temperature. Now, one of the things that happens is no resistance. Another thing that happens is that you don't lose any energy because there's no resistance if electrons go down a wire. Now, in your toaster, you want electrons to lose their current. You want to heat up the wire to make the toast. So electrons traveling down an ordinary wire will bump into impurities and into vibrations and so forth, and it'll generate heat. But electrons in a superconductor will go through with zero resistance. Not a little resistance, zero resistance. And as they come down, when an electron bounces off an impurity, another electron bounces the other way to take up its loss. And I'll show you this in a moment. The curious thing is that if you get a ring and you make that ring superconducting, not only will the electrons travel around with no resistance, if you keep it cold, it'll keep going like that again for the age of the universe. It just won't decay. It'll keep going. But it traps a magnetic field because a coil will make a magnetic field. And so if you had a room temperature superconductor, you could trap magnetic fields, send them all over the country on railroad cars or whatever. And in fact, it pushes out any other magnetic field. So this is a demonstration that I didn't have time to actually set up. But this is just a little saucer of liquid nitrogen. And in there is one of those yttrium, barium, copper oxide superconductors. And this little train, which is actually a picture of a train, these are just magnets. And because the magnets put out a magnetic field and the superconductor won't let the magnetic field in, the train levitates. And people are building trains that are levitating above the ground. And I've been levitated in Texas. I stood on one of these magnets and they cooled it down, and then all of a sudden you rise. And these trains can travel at 300 miles an hour, and there's almost no friction here. So if we can get the superconductors at higher temperatures, it would be an incredible technological advance. So why does this work? Well, the idea is the following. You agree that you're going to go to a dance, and you agree that your partner and you will stay 15 feet apart. Not that you don't like each other, but it's part of the game. If you move forward, your partner moves forward. If you move back, your partner moves back. And between you and your partner, since you're 15 feet apart and there are a lot of people around, there are other people. So if you come late to the dance, you see sort of a swell of people going in and out all over the place. But if you look carefully, you'll see that the pairs, are moving opposite always to each other. So for example, this electron is moving this way. This one has to move the other way. They're together. This red one, this red one. But this green one, if it bumps into anything, the agreement is that its mate has to go the other way. And because of that, the electrons can move down the wire, and no matter what they encounter, whatever price they pay, their mate will pick up the check, sort of, to take care of it. So I actually went over to the dance department of Berkeley and got the students we did choreography for this, and did sort of the dance of the electrons, and it was part of a Nova show, and it was our 15 minutes of fame. It actually made it to the cover of Le Figaro in France, and this is what the students looked like, and it was really very impressive to see them bouncing off each other, and it illustrates how this works. Now, in 1987, this copper oxide was discovered, and it's a high-temperature superconductor. And despite the fact that we can explain superconductivity in aluminum and lead and many other materials, and despite the fact that that theory is now 50 years old, I just went to a Bardeen, Cooper, Schrieffer theory of superconductivity anniversary, 50-year-old anniversary at the University of Illinois. That theory explains all the properties of superconductors, but these new copper oxide superconductors still not explained. There are dozens of theories out there, and there's no consensus. And just before I went to give a talk, because that's a 20-year-old theory, this cartoon came out in the New Yorker where we picture ourselves as the theorists and confessing to our psychiatrists that even though there are a lot of theories out there, we don't have a theory of high-temperature superconductivity right now. Now, that's unfair because there may even be people here who have a theory. And there are many people over there, but there's no consensus on the theory. So that's one of the openings for some of the young people to come into our field and tell us why the copper oxide systems have such high transition temperatures, because we're trying to boost them. We're trying to get the higher temperature superconductors. And there was a meeting this summer in Norway called the Road to Room Temperature Superconductivity. And, of course, no one came in with a room temperature superconductor, but people came in with a lot of ideas, and we don't know which of these ideas are right, which brings me to my last Einstein quote, which is my favorite. And he said, the most valuable tool of the theoretical physicist is his wastebasket. Thank you very much.